Hello, my name's Amber Stuver. I'm a physics professor at Villanova, and I specialize in observing the universe in a brand new medium called gravitational waves. Thank you very much for having me today, and I look forward to answering any questions you have about my presentation. So let's go ahead and get on with that. So my talk today is about probing the depths of the universe with gravitational waves. I'd like to start with a poem by Walt Whitman, which was written in 1865, titled "When I Heard the Learned Astronomer." When I heard the learned astronomer, when the proofs, the figures were ranged in columns before me, when I was shown the charts and diagrams, to add, divide, and measure them, when I sitting heard the astronomer where he lectured, which with much applause in the lecture room, how soon unaccountable I became tired and sick, till rising and gliding out, I wandered off by myself in the mystical, moist night air, and from time to time looked up in perfect silence at the stars. So while Walt Whitman is one of my favorite poets, whenever he wrote this poem in 1865, we weren't aware that there were any galaxies other than ours, other than the Milky Way. And the same passive awe he has and feels, he doesn't understand that this is the motivation for the active awe that the astronomers are pursuing. And the result of this active investigation into the stars can lead to knowledge, which is often just as inspiring as the initial inspiration that Walt Whitman is talking about here. He feels that because the astronomers are in a lecture hall and poring over numbers, trying to understand more about what the stars are and how we fit into the universe as a whole, that the astronomers don't hold that same awe, that they don't go out and look at the stars. And that's just fundamentally untrue. And I think that is important whenever thinking about astronomy and seeing that as a way of viewing our role in the larger history of the universe. And one of the things that allows astronomers to pore over numbers and to understand how the universe works is the universality of physical laws. And that is that physical laws of the universe apply throughout all of the universe, throughout all of time. So the laws of physics and chemistry that we observe here on the small scale in our labs, these laws also describe the stars and everything else in the universe. So just to give a few examples, elements give off very specific colors of light when they are electrically excited. Helium was actually first discovered on the sun as a yellow color that was observed in a solar flare in 1868. And this is an example of the spectrum. So this very specific colors that helium gives off. And it's that yellow color, which was the signature that was observed in the solar flare in 1868. And helium was only later observed on Earth in 1895. So we took a physical law that we had discovered here on Earth in a lab. We applied it to our own star, the sun. We found something new first on our star, and only later did we find that helium was also present on the Earth. And to me, that's just fascinating. We also know that the universe is expanding because these same colors are given off by all of the elements, including hydrogen. And hydrogen and helium are two of the most abundant elements in the universe, with hydrogen being the most abundant. So we can look at the specific colors of hydrogen and see that the spacing between the specific colors is always the same, but sometimes it's shifted towards the red end of the spectrum. So we can see a Doppler shift. That's what's causing this shift in these spectral lines. And it's almost always towards the red end of the spectrum. And that means that the colors, so the wavelengths of light, are getting longer. And that can only happen in Doppler shifts whenever things are moving away from us. So we see that almost the entire universe is moving away from us. And the farther away something is, the faster it is moving away from us. And I say almost everything because there are a few things that are local to us that we're gravitationally bound to. For example, the Andromeda Galaxy. It is moving towards us. In about 5 billion years or so, the Andromeda Galaxy will be approaching the Milky Way galaxies, and our galaxies will merge someday in the future. And to be perfectly honest, that would be a spectacular sight to see in the sky. Our own Milky Way and the Andromeda Galaxy interacting. That would be quite awesome. We also know the temperature of stars based on the brightest color that the star gives off as a whole. So again, color is also a way of saying a wavelength of light. And the understanding of that came from our understanding of blackbody radiation. As things get hotter, the peak wavelength or color of light they give off changes. And you've actually observed part of blackbody radiation whenever you have seen the coils inside of your toaster oven turn red as they heat it up. So astronomy fundamentally probes the history of the universe because the speed of light is finite. It's not infinite. Light takes time to travel from place to place. Therefore, the farther away an object is, the farther back in history we are observing. Everything we see is in the past. Well, I'm obviously in the past because this is a recording, but the sun in the sky is about 8 minutes and 20 light seconds away from us. That means the sun that we are seeing in the daytime sky, that light that is entering our eyes at any given instance, left the sun 8 minutes and 20 seconds ago. And it only gets to be a longer, farther back probe into the history of the universe, the farther away the object that we're looking at is. So our current limit based on light observations is the cosmic microwave background. And this is the relic light from about 300,000 years after the Big Bang. And this 300,000 years after the Big Bang is a time whenever the universe became transparent. So whenever electrons started binding themselves to atoms, light was able to travel through the universe without being immediately reabsorbed. So using the cosmic microwave background, we can see pretty far back into the history of our universe, but still we're hitting that wall of 300,000 years after the Big Bang. What happened that? How are we going to probe that? And there is potential to push past that wall with gravitational waves. So the universe became transparent to gravitational waves about 10 to the negative 36 seconds after the Big Bang. So that is a 0, a decimal place, 35 zeros, and a 1 after it, seconds after the Big Bang, essentially the instant after the Big Bang. And if we can observe these relic gravitational waves, they will be able to teach us much more about the early universe than the cosmic microwave background will be able to. So I've already introduced the words gravitational waves, but what are gravitational waves? So gravitational waves are often referred to as ripples on space-time. And to get a good idea on exactly what space-time is, I gave an example movie off to the right here. And what you're seeing are two neutron stars that were orbiting around each other, and then they merged and they became a black hole. Underneath these neutron stars, you see a green grid. This is an abstraction of space-time. And you can see that there are waves in this space-time. And what space-time really is it tells us about the strength of gravity at any given place in the universe. So in this example of space-time, the greater the slope of space-time at any point, the greater the gravity at that point. And these waves that we see moving from the neutron stars on space-time, those are basically just waves of gravitational field, waves of information traveling through the universe, telling masses the changing gravity they should feel because of these two neutron stars orbiting around and moving around. So that is fundamentally on a more elementary level what a gravitational wave is. Every mass that accelerates will create a gravitational wave. And this is very much like how accelerating charges are able to create electromagnetic waves or light. So gravitational waves are the analog to light in gravity. So light comes from the study of electricity and magnetism, and gravitational waves come from the study of general relativity. However, gravity is the weakest of the fundamental forces in the universe. So it's the glue that holds the universe together because there is no negative mass like there is positive and negative charge, or in magnetism, like how there's a north and south pole. There is only positive mass. So we're never going to be able to cancel out a gravitational field with a negative mass. And no, we don't know why there is no negative mass. We have looked, there just isn't, at least as far as our observations have gone, even probing into the universe. So because gravity is so weak, only extremely massive energetic events will produce detectable gravitational waves once they reach us here at Earth. So obviously, there is nothing extremely massive or energetic nearby us, or our solar system would have been disrupted long ago, and we would have much bigger problems than worrying about detecting gravitational waves. Some examples of these massive energetic events would be the Big Bang, the supernova explosion of a dying star, compact binary merger, which is actually the technical term for what I'm showing you on the screen right now. Compact just means things that are not are more dense than normal stellar matter. So things like neutron stars, like what is in the illustration here, or black holes are good examples of compact objects. So whenever those objects orbit around each other and they get closer together and they start orbiting faster and faster, like a figure skater that starts with their arms spread wide and then they spin faster and faster as they pull their arms in. That is the same kind of situation that will produce strong enough gravitational waves to be detected here at Earth. So how do gravitational waves affect space? So gravity is a tidal force. And that means it will locally compress space in one direction and expand it in an orthogonal or 90-degree direction. And I have an animation of that here so you can see side to side. As the side to side compresses, up and down expands. And as up and down compresses, side to side expands. So this is the effect a gravitational wave would have as it travels through the universe. And knowing this, we need to if we want to detect gravitational waves affecting us here on Earth, we need to build a detector that is sensitive to these kinds of changes in space as a gravitational wave passes. And in the United States, there are 2 detectors that can do that. These detectors are jointly called LIGO, and LIGO stands for Laser Interferometer Gravitational Wave Observatory. And we have 2 in the United States. There's one in Livingston, Louisiana, and that's pictured on the left. It's in a swampy pine forest. And there's another one on the Hanford Nuclear Reservation in eastern Washington State, and you can see that on the bottom right. They are both L-shaped detectors, and they continually measure the length of each arm and compares them to each other. If one arm gets shorter while the other one gets longer, that could be because a gravitational wave is passing by. And these detectors are very large. So the larger your detector is, the more sensitive you're going to be to gravitational waves. And so each of these detectors, you can see that they each have 2 arms, and both arms don't fit in either one of these illustrations, but you are able to see one arm from each. Each of those arms is 4 kilometers long, or in our everyday experience here in the United States, that is very close to 2.5 miles. In 2015, actually very specifically, on the 14th of September on 2015, at about 5 o'clock in the morning, local time in Louisiana, we saw the data that you see on the left here. And this is actually kind of the type of signal that we would look for whenever we are looking for 2 very dense objects orbiting around each other and then merging. And just a little while later, we saw this signal in the LIGO Hanford detector. As you can see here, these 2 signals are the same signal. It's actually one of the reasons why we have 2 LIGO detectors. One of the best ways to be sure that you aren't being tricked into thinking something is a gravitational wave whenever it actually has an origin from the Earth is to have 2 detectors that are located very far apart from each other. That way, any local noise, say trains, vibrations, people dropping hammers nearby, things like that, they're not going to affect the other detectors. So the noise in each one of these detectors is independent. However, a gravitational wave will affect both of these detectors in nearly the same way, with a very slight delay because of the time it would take a gravitational wave to travel from one detector to the other. And for the 2 LIGO detectors, they are located almost exactly 3,000 kilometers apart. So the maximum time it would take for a gravitational wave to travel between the 2 detectors is about 10 milliseconds. And so this is well within that time. And so we were really excited. This was actually the very first day that we had used our detector, well, our upgraded detector, to start looking for gravitational waves. We took several years off of observation to make our detector much more sensitive. We commissioned it, and essentially the first day we turned it on, we found this, and it was extraordinarily exciting. Almost so exciting, we almost couldn't believe that it was real. And we did spend the next 5 months before we told anyone about this, trying to prove that it wasn't. That's another thing about science. You can never prove that something is true. You can only prove that something is false. And if you cannot prove something is false, you can only measure your confidence in your observation. So we spent the next 5 months building our confidence that this was a real gravitational wave. And what I just superimposed on the 2 signals that you are seeing on the screen now is what is predicted from a gravitational wave from 2 black holes One was about 35 times the mass of our sun. The other was about 30 times the mass of our sun. And they were orbiting around each other hundreds of times per second, emitting these gravitational waves before they merged, and then the gravitational wave signal ended. These gravitational waves specifically originated about 1.3 billion light years away. That means that these gravitational waves had been traveling for 1.3 billion years before they were incident on the Earth on the day we happened to turn on our detector for the first time in a way that was able to produce quality science. And to give an idea of exactly how long 1.3 billion years is, whenever these two black holes merged, what was going on here on life was the formation of multicellular life. There were no animals on Earth yet. And that gravitational wave traveled, and we just happened to be ready to catch it whenever it passed by Earth. If you were able to see this, which you would not, this did not produce any sort of light, either visible or in any of the other wavelengths of light, you would have seen something like this. What you're actually seeing is a galaxy background with a simulation of our two black holes that made this gravitational wave signal. They're the black holes that were moving around. And as they move around, their gravity is so strong that they are able to warp the space-time around them and warp the light around them. This is called gravitational lensing. So if we were able to see this, if we were some very optimal place in the universe and we had a God's view of this, this is what it would have looked like slowed down about 100 times. So these are two black holes going around each other, and they eventually merge. And one of the things I find very interesting is you'll notice there's an outer ring. And even after the black holes merge, if you look closely at that outer ring, you're going to see some stars wobbling back and forth. So, okay, there's the merger. And if you look at that outer ring, you can see some stars wobbling back and forth. So the black hole in the middle isn't moving anymore. What actually is causing those stars to wobble back and forth is the gravitational waves propagating out into space-time. You're actually seeing gravitational lensing from the gravitational waves that are passing by. And that's just amazing that these two incredibly massive black holes were able to produce gravitational waves of such strength that locally they could have warped space-time so much that the light would be bent just because of the gravitational waves. And then by the time they reached here at Earth, 1.3 billion light years away, we were able to detect them with our detector. So a few years later, on August 17th of 2017, there was a neutron star binary. And a neutron star, again, is a dead star that is very compact. And whenever these neutron stars orbit around each other, it was actually hypothesized that a merger of these two neutron stars might be able to produce something called a short gamma ray burst. There are two kinds of gamma ray bursts. One's a short and one is a long. We have evidence that the formation of a black hole from a collapsing star can create long gamma ray bursts. But we didn't really know what could create a short gamma ray burst before this. We had hypotheses, and one of those hypotheses was the merger of two neutron stars. But a hypothesis is just a hypothesis until you get some evidence. And so on the morning of August 17th, we made these observations. This is the sound of the gravitational wave. So there's the merger. And that little ding was the detection of gamma ray bursts from an orbiting satellite called Fermi. And this was about 1.2 seconds after the end of the gravitational wave signal. So just to back up a little bit, gravitational waves do not make sound. Sound waves are fundamentally different than gravitational waves. However, the frequencies of the gravitational waves that LIGO is able to detect are the same frequencies that human ears would be able to hear if we turn them into sound. So what we do is we take the signal coming out of LIGO and we put that electric signal through a speaker, just like any other music signal that you would put out from your radio. So right after that, 1.2 seconds later, there was a detection of gamma rays. And this was extraordinarily exciting. It could have been coincidental, but further investigation showed that it wasn't. These two were associated with each other. So we want to find the source of these two these associated signals. If they came from the same event, then they're going to come from the same part of the sky. So we were looking for we were looking for the source using the information from each of the instruments that observed it. So this is an illustration of the sky. That is the area that the Fermi Gamma Ray Telescope was able to isolate it. There is another telescope called Integral that was able to isolate it to that band on the sky. The two LIGO detectors that were operational at the time were able to isolate it to those two green lobes. And the Virgo detector is also operational. Including it gave us this smaller area on the sky. So inside that smaller area on the sky are a fixed number of galaxies. And it just so happened that one of those galaxies had a new star in it that we were able to observe. So we were able to isolate that the gamma ray burst and the gravitational wave source came from this same location. So on the side, on the left here, the galaxy that specifically hosted this neutron star merger was a galaxy with the name NGC 4993. Really catchy name, I know. It's about 130 million light years away. And inside the search area that we just saw on the last slide, there were 49 galaxies that were in that area on the sky. And within the distance range that we were able to estimate from the gravitational wave detections, we were able to estimate how far away the gravitational wave came from. So instead of having an area on the sky that we were able to say that this source came from over there, we were also able to say what the depth into the sky was. So essentially we had a volume in the sky to search. And the traditional astronomers with optical telescopes, or should I say electromagnetic or light detecting, they're not all optical or visible light. In that search volume, there were 49 galaxies. They sorted them by mass because the more mass a galaxy has, the more stars it has, and the more likely it is for something like this to happen. And this was third on the search list to be observed. So this was found relatively quickly. And what I'm going to show you is on the left here is our galaxy NGC 4993. And this is actually right now an archive picture taken 1,225 days before our actual event. Whenever I start the video will start playing. You will see a new star come into the picture. It'll initially start off reddish color, and as time goes on, it's going to dim in brightness, and it's also going to change color to be more blue. And the brightness and the different wavelengths of light coming from this new source, and remember, wavelength also corresponds to color, is going to be plotted on the right. So now you're able to see this new star, and it's getting dimmer and dimmer as time moves forward, and redder and redder. And on the next playthrough, I'd like you to focus on what we call the light curves on the right. So it starts off very bright, and then it dims, and it becomes more blue, but there's also some peaks here. And those peaks between about 1 to 1.6 micrometers, those specific peaks, these are the spectral signatures of heavy elements being created. And what I mean by heavy elements, elements heavier than iron on the periodic table. So stars using fusion are only able to fuse together lighter atoms up to iron. That is able to produce energy to fuel the star. After that, the star begins to die because it has run out of fuel. So only iron can be made through normal fusion in a star. And astronomers for a long time wondered, where did the other heavy elements coming from around us actually originate? Did they originate in supernova, where runaway fusion reactions can happen that can create these heavier elements? Looking around just our local universe, there is much more heavy elements than there should be just from stars exploding. And so here, what we're seeing is the merger of two neutron stars is creating heavy elements. And the estimates of how much heavy elements was created was about 10,000 to 16,000 Earth masses of heavy elements. And with this amount of heavy elements being produced, this is enough to explain what's around us in the universe, what we observe in our universe. If this happens in every galaxy once every 10,000 years, and this is actually a very feasible rate. So the heavy elements that are around us. So a good example of that might be the silver or the gold in any jewelry that you have. Not only could have been made in a supernova, it could also have been made in the merger of two neutron stars colliding and creating this explosion, which is called a kilonova. So what we're seeing here on this illustration is a signature of this explosion from the two neutron stars called a kilonova, which creates heavy elements. So specifically, if we redo our periodic table of elements, you can look here and see how each of the elements was predominantly made. So if we look here at gold and silver, we can see that the bigger area of their spot on the periodic table is going to be this orangish color, yellowish color, excuse me. And this yellowish color comes from the merging of neutron stars, and a smaller portion comes from dying low mass stars. So actually, heavier elements, things like silver and gold, your jewelry, is most likely, most of it came from the merger of two neutron stars, and maybe some of it came from a supernova explosion. And going back to Walt Whitman's original opinion about the active investigation, the active awe that the astronomers had, I wonder what kind of awe he would have had, not only learning that there are billions upon billions of other galaxies in the universe, but also the gold and or silver in his pocket watch probably originated from the depths of space, from these incredibly energetic, massive events that had happened deep in the history of the universe. And that is just in his pocket watch. I wonder what kind of awe he would have had if he had known those things. And recently, there has been a new way to observe gravitational waves. And this involves something called pulsar timing. Pulsars are neutron stars that beam out light from their magnetic poles. So the neutron stars are spinning very rapidly. And if that beam of light coming from their magnetic poles happens to sweep across the Earth, we're able to observe it like we would observe the light from a lighthouse. And some pulsars are so predictable that they are actually more accurate than atomic clocks here on Earth. And we can use the timing of very slight delays in the arrival of these pulses to indicate that the distance between us and that pulsar may have increased, not because they are actually moving away from us, but because space-time was warped between us and them by a gravitational wave. So these pulsar timing arrays, so looking at many different pulsars and doing coordinated timings between them, these experiments are designed to discover how galaxies merge and grow throughout the history of the universe. LIGO is looking for gravitational wave from short duration transient sources. They come and they go. These gravitational waves that the pulsar timing arrays are looking for are from merging galaxies, which almost all galaxies has a supermassive black hole at the center. And these supermassive black holes at the center of merging galaxies will begin to orbit and create gravitational waves. And the merging galaxies from all over the universe will be producing gravitational waves simultaneously. So pulsar timing arrays aren't measuring single gravitational waves like LIGO is. They are measuring many gravitational waves coming from all over the universe where these supermassive black holes are orbiting each other. In the United States, the collaboration that looks for these pulsar timings is called NanoGrav. Nano because it's looking for gravitational waves that have a frequency on the order of nanohertz, and grav because they're looking for gravitational waves. So these signals are extraordinarily long duration signals. So we're talking millions of years in order to make a complete period. And recently, it was announced that there is strong evidence that these pulsar timing arrays have detected the gravitational waves from these merging supermassive black holes. So they're not necessarily merging as in touching yet, but they're orbiting each other and will eventually merge in the future. And they have a confidence of this of about 99%. So there's about a 1 in 100 chance that this would happen by accident. More data is necessary in order to get to the very, very high standards for an absolute detection, but this is an extraordinary observation by itself. So continued observation is going to increase the confidence of these observations and possibly help us resolve the sources of these supermassive black holes that are making these gravitational waves on the sky. And because of this, we're going to then be able to look at learn more about how galaxies have merged throughout the history of the universe. So fundamentally, astronomy, especially new astronomy with gravitational waves and any other kind of new astronomy that looks at the universe in a new way, lets us see our place in the universe in a new way, lets us understand the history of the universe in a new way. So specifically for gravitational waves, we can find out about the nucleosynthesis or creation of heavy elements. We can find out more about fundamental physics. So far, we've proven that a gravitational wave indeed travels at the speed of light within 1 part in 10 to the 15. We can learn more about cosmology. We can make independent measures of the Hubble constant. And even more, we can detect gravitational waves from the earlier universe itself. So the current farthest away detected gravitational wave is 8.4 billion light years. That is 61% of the age of the universe ago. So gravitational waves truly do offer the ability to probe the deep history of the universe. We can learn more about neutron star physics. We can learn how that dense compact matter behaves. And we can also learn more about gamma ray physics. So I mentioned earlier that we knew that long duration gamma ray bursts could be formed from supermassive stars exploding and forming a black hole, but we only had a hypothesis that merging neutron stars could create the short gamma ray bursts. But with the observation we have made that I showed you a few slides ago, we actually have our first evidence that supports that hypothesis. So now we know that it is possible for a neutron star binary system to merge and create a short gamma ray burst. Is that where all of them come from? We still don't know, but we do know it is in fact a valid progenitor for these short gamma ray bursts. So thank you very much for your time and your attention. I very much appreciate it. I'm very passionate about what I have essentially spent my career doing. And it really bothered me whenever I was in high school reading Walt Whitman's poem that I shared with you at the beginning. And I have learned from becoming an astronomer myself that he is mistaken that we don't have that awe that he has to learn about, to gaze at the sky and wonder about our place in the universe. We're just much more active about finding out the details, and that active awe can actually give you much more to be in awe about and many more questions. So thank you very much, and I will be happy to answer any questions that you have.